you've got to use the E button on this. So we plugged all this in. We've got 3.03 times 10 to the 19th, negative 19th joules. That's the energy for it. Down here, we just need to plug these guys in. So if we take negative 2.8 and divide it by 5 squared, we get negative 8.72. And I've actually already got these answers, so I'm going to just plug these in real quick for you. So that's negative 8.72 times 10 to the negative 20th. All these are going to be joules. This is negative 1.36 times 10 to the negative 19th. And this is negative 2.42 times 10 to the negative 19th. Out of these two right here, negative 2 or negative 1, which one is the bigger number, the greater number?
Negative 1.
Negative 1, right? Since these powers are the same, that's easy for us. Negative 1 is closer to 0. Negative 2 is closer to 0. How about negative 1 or negative 8? Which one is the bigger one? If we had negative
8.
If we had negative 1 and negative 8, negative 1 would be bigger. But we can't look at this as negative 8. We've got to look at it as negative 0.08. Now, I know it's 0.000, a bunch of 0.8s. But when we compare these two, this is 0.08 versus 1. So this is a much smaller number. But the fact that it's negative means it's bigger because it's closer to 0. Strangely enough. So our order here is that order right there. This is the order. The energy of the first electron ring is less than the second, is less than the third, is less than the fourth, is less than the fifth. And I don't need that last mark for some reason. So the further away from the nucleus you are, the more energy you have. We've shown that with nunchucks, or if you swing in a lasso or anything else, the further it gets out there, the more energy it has. Just like a bat. When you swing a bat, you want to hit with the furthest part from you on the bat. You don't want to hit it close to your hands. So this now allowed us to find the energy of the photons up here with these equations. This allowed us to find the energy that each electron would have in these different energy levels. So then we have that amount. If we take a look here, we can calculate the energy of the photon when an electron basically leaps down to a lower energy level after it's been excited. This is called the quantum leap. So if you've heard the term quantum leap, that's what's happening. An electron has been excited. If here's the nucleus, the electron has been excited. And when it goes back down to its original state, or what we call the ground state, it emits a photon. That photon has a certain amount of energy, which means that it has a certain frequency or a certain wavelength. And if we can find the energy of that photon, we can find the wavelength of light that's emitted. All we got to do is a little bit of subtraction. So 5 and 3. Well, that's our negative 8.72 times 10 to the negative 20th minus, if you're wondering where I'm getting these numbers from, we just got these numbers, right? Minus the negative 2.42 times 10 to the negative 19th. This is absolute value, but we know it's always going to be positive because we're always subtracting the higher level from, we're always subtracting the lower level from the higher level, or higher level minus the lower level. So negative 8.72 times 10 to the negative 20th minus negative 2.42 times 10 to the negative 19th. Boom. We get 1.58, 548, which rounds to 1.55 times 10 to the negative 19th. Make sure my numbers are correct on that since this is the first one I'm doing. Looks correct to me. Anybody have any other answers that they got for that? If you tried it. All right, so for the next one, what are we gonna do? Well, we're going to subtract the second energy level, which is negative 2.18 times 10 to the negative 18th. Both of these also are in joules. So that means we get joules as our final unit. And we're gonna subtract this from the fourth principal energy level, negative 1.36 times 10 to the negative 19th joules. Remember, you can add and subtract apples from apples or oranges from oranges or joules from joules. And you get joules in the end.
Is that the second one?
So the fourth, 1.36 times 10 to the negative 19th. And the second energy level, negative 2.18 times 10 to the negative 18th. Does that answer your question?
Wasn't that the first one, negative 2.18?
Oh, thank you. Look at this. I got so used to reading it from here, I read it from here and I didn't look closer. It's divided by 2 square, which makes it, thank you guys, negative 5.45 times 10 to the negative 19. Good call. Good thing I brought some white out from school. I don't know how much I have of this. I better be not making as many mistakes. Minus negative 5.45 times 10 to the negative 19. All right, so let's go ahead and plug that into the calculator. Negative 1.36 times 10 to the negative 19th minus negative 5.45 times 10 to the negative 19th. Boom. 4.09 times 10 to the negative 19th. So that's the energy of a photon that has quantum leaped from the fourth principal energy level to the second principal energy level. Phew. It's gone back closer to the nucleus. In order to do that, it has to release this energy. That energy is in the form of a photon. If I wanted to find the wavelength, 1, 2, or 3, which of these equations would I use to find wavelength?
Two.
2. I have the energy of the photon. I know Planck's constant. I know the speed of light. That gives me lambda. I'm going to have to rearrange it. And that's actually what question 5 down here is. So if we have the energy of the photon, Planck's constant, and c, how do I rearrange this equation to solve for lambda? What do I need to do to both sides?
Don't you multiply them both by the lambda and then divide by energy of the photon?
You're exactly correct. We're going to multiply by lambda and divide by energy of the photon. That rearranges our equation to solve for lambda equals hc over EP. So I'm going to write that down here. 6.626 times 10 to the negative 34th joules seconds times the speed of light, 3.00 times 10 to the 8th meters per second. And then we're going to divide that by the energy of the photon. In this case, 4.09 times 10 to the negative 19th joules. What are my final units going to be for this?
Meters.
Meters. Joules will cancel out, seconds will cancel out. We will be left with meters. So my final unit's going to be meters. Let's go ahead and plug that into the calculator. Again, I always suggest You plug anything I plug into the calculator into there. That way you can check my answer in case I messed up something. And you know for sure that you know how to use the calculator. You get 4.86 times 10 to the -7th. Meters. Now, if you're not in scientific notation, that may actually look like this, right? It's the same thing, just different notation. So you want to make sure you're in scientific notation. Boom. That's a very, very small amount of meters. So instead of using this, it might be better if we use nanometers. Does anybody remember from the summer packet how many nanometers are in a meter? No.
Million?
A million is micro. So what's the next best guess? It's not a million, it's a
1,000?
nope,
Billion?
billion. There are a billion or 10 to the 9th nanometers in 1 meter. Has your math teachers taught you how to do this? If you have 10 to the -7 times 10 to the 9th, that becomes 10 to the what?
The second.
Yeah, the second. So they've taught you that. Basically, you just have to add these exponents.
Yeah.
So that's 4.86 times 10 to the 2nd, or 486 nanometers. Well, what does that tell us exactly? Well, the cool thing is that electromagnetic radiation, if we take a look here, it starts off down with the radio waves. You guys probably don't know what UHF and VHF TV is. When I was growing up, about your age, we didn't have cable. You had UHF, which were basically the channels above 15. So that would be, it was always WX something. And basically, what is that? Fox 59 in Indianapolis, if you know the channel Fox 59, that would have been in the UHF category. All the other channels, ABC, NBC, and CBS, are in VHF range. You used to actually have a little thing, you had to switch from UHF to VHF. Anybody want to have any clue of what VHF is versus UHF? Does anybody know what FM means when we say FM? No? So that's frequency modified. VHF is very high frequency. Anybody for UHF now? What's better than very?
Unbelievable.
Unbelievably high frequency?
Ultra high frequency.
Ultra high frequency is correct. Very nice. Who said that?
Amari.
Mari, very good. Unbelievably high frequency would be amazing, but it is ultra high frequency. And then you have radar, and then you have microwave radiation. And keep in mind, we are getting higher and higher in frequency, which means we're getting shorter and shorter and shorter in wavelength. The shorter the wavelength, the higher the frequency because of that speed of light equation from before. Here's the cool thing. Microwave radiation, you have this in your house. You have what's called a magnetron in a little box, and that magnetron vibrates and sends out these microwaves. Those microwaves cause the water molecules to start vibrating. When those water molecules vibrate, they rub against each other. What happens when they rub against each other? Just like when you rub your hands.
Creates heat.
Yeah, right. When you rub your hands together, that's friction. Those water molecules rubbing on each other, they're going to create friction and heat up those particles, right? Kinetic energy. Just above that is infrared. This is IR. If you've got that remote control, now's the time, pull it out. Who's got one? Turn your camera on if you got one. Let me see here. Gavin's got one. All right. So we're going to go to, I'm going to go to speaker mode. To do that, I've got to stop sharing real quick. And if you would, Gavin, there we go. Gavin, what I want you to do is I want you to point that at the camera. And I want you to press the button. See that on the camera? Press it one more time. Now, Gavin, I want you to look at it. Look directly at that with your eye and press the same button. You see anything? No, because you actually can't see that. You can see it here, right? But you can't see it visibly because that's infrared. Our eyes cannot pick up that infrared. The camera can pick up that infrared and then change it into something we can visually see. It's kind of cool. We can't see it, but the camera actually can, and it actually makes it into something visible. You could walk into a room that was completely dark to you, but there's an infrared light in there. That means that if there was a camera in that room, it would see everything. They use this for haunted houses. To tell you the truth, those of you that wear leggings and stuff like that, the infrared camera can penetrate through those leggings and give the infrared rays can penetrate through those leggings. And if a camera reads that, then it's going to look like you're really not wearing anything. They actually are using this in airport security and stuff like that to determine whether or not somebody has a weapon or something stashed to them. They use such high intensity that it penetrates through multiple layers of clothing and gives an image of basically, what's beneath it. So just keep that in mind if you're wearing leggings to your next flight, whenever your next flight's going to be. There may be a different image of somebody that somebody is looking at. They use it in haunted houses to protect like the actors and to make sure that the actors are doing everything correctly, because haunted houses are usually dark, but the infrared, the camera doesn't care. The camera can see it. Let's go on up further in frequency. Oh, there it is. Hit it for myself. All right. Yeah, you can try that later. If you didn't have one on you now, you can do it. Actually, to tell you the truth, your phones, where is it? I can't do this. Your phones actually send out an infrared signal quite a bit. It's that little light up there by your speaker. Let's see if I can get mine to do it. I can't seem to do it, but it'll sit there and send that out and flash that out. And basically it's trying to search for your face and stuff. So above infrared, frequency wise, what do you think we have? Infra means below, inferior, right? Below, infrared. So right there, we get into our visible spectrum, and that's where we have red come in. If we take a look, if you have a cheap laser, you can actually look on there and see, it'll tell you, unfortunately, these cameras, the digital cameras can't pick it up, but it'll tell you the wavelengths that it gives out. This is a wavelength of 620 nanometers to 650 nanometers. Well, 620 nanometers to 650 nanometers is what color? Red, right? So if we take a look, that gives us off a red laser beam. If we had a laser of 486 nanometers, what color would that be? Here's 420, 440, 460, 486. That would be a green laser. Green lasers are called stargazing lasers because our eyes see green very well. And you can, if you get one of those green lasers, you can sit there and point it up and you can say, hey, look at that star up there. And it will actually shine up into the sky and somebody can sit there and follow which star you're actually looking at. Pretty cool. Right in the middle of our spectrum, if you see right here, this yellow, in Europe and Los Angeles and New York, I think New York, maybe not New York. I know at least Los Angeles and over in Europe, their emergency vehicles are this color because that's the color that's right in the middle of our spectrum. And we can see that color very, very well. And then you get to blue, a blue laser for like your Blu-ray player or your PlayStation or Xbox. That's going to be here in the 438, I believe-ish. And then you have violet. And guess what is above violet? Davis. Unbelievably violet?
Ultraviolet.
You got it. Ultraviolet. We can't see ultraviolet either. We can't see all the rays that come from the sun that excite our melanin production in our body. And then above ultraviolet, you have X-rays. The frequencies here are so small, they can get between small fractures in your bones. The wavelength is so short, they can creep right in between parts of, like if there's a fissure in your bone. When they do that, they excite the film behind it and they expose it. And that's what we use to see, bone fractures, bone breaks. They have no trouble getting through your skin. Your bone is pretty dense, so most of your bone will block it. But if there's fractures or breaks in your bone, they'll get right through there. And then we have gamma rays, which have no trouble getting through you really at all. Gamma radiation. So that is the electromagnetic spectrum, or the EMR spectrum. So this light right here, this would be green. For this evening, I would like for you to complete a C and D. And then I would like for you to do number 6 and tell me what color it is.
So will we just look at the little color thing on, like the nanometer thing on Mark?
Yeah, if you want, I can, you could go back to this video and pause it, obviously. But basically 400 would be blue, 500 green, 600 and above red. It's gonna be either green, blue, or red. And we've already taken care of red, right? Oh no, we've taken care of blue. I'm sorry, green. Questions there? Well, that was my goal for today. We completed it. If we take a look at what we're doing tomorrow, we talk about the last unit, periodicity. There are 3 major things that we're going to talk about for periodicity. And then basically we have review. Again, as I said, we're not going to have a test over just this unit. It will be covered on the final exam. If you have any questions, by all means, stay in the Zoom. If you do not, have a great day. Take care. You've got, I'm gonna keep hiding this from myself. You've got 12 minutes to do those other problems. Have a great day, guys. Bye. Bye. Thanks, Gavin, for having that.
No problem.
Mr. Jackson, I got that ideal gas law homework resubmitted.
You do? Excellent.
Yep.
So I'll,
thank-
it should give me a notification, and then what I'll do is I'll grade it probably by Friday.
Okay, thank you.
You're welcome. Have a great day.
Oh, with my two